Hello, Matthews, Gatos here. In this video, we're going to cover section 6.3, but before we do that, I just have 3 diploma examples I want to go over of section 6.2 as a nice review. So in the first one here, the expression of sine pi over 2 minus theta plus cos of pi over 2 plus theta is equivalent to which expression? So multiple choice question, and I have adding and subtracting. So I'm going to go to my formula sheet, and I have the adding and subtracting parts that I want to use. So let's look. For the sine where I am subtracting, I'm going to use this one right here. So sine of pi over 2 minus theta is going to become sine of pi over 2 cos of theta minus cos of pi over 2 sine theta. So let's just tidy this up before we go on to the cos part. So sine of pi over 2 and cos of pi over 2. If we look at our unit circle, the coordinate pi over 2, or the point pi over 2 on the unit circle, has a coordinate of 0 and 1. It is a y-intercept, which means that cosine is 0. So 0 times anything gets rid of that. And sine of pi over 2 is 1. So I'm going to have 1 times cosine of theta. So this whole thing, because it's subtracting 0, is just cos of theta. Okay, so this right here is cos of theta. Let's work out the other part here. So we're going to do cos of pi over 2 plus theta. So that's going to be this one right here. So let's substitute that in. So I'm going to do cosine of pi over 2 cosine of theta minus sine of pi over 2 and sine of theta. So again, we saw that cosine was 0, so this is 0, and 0 times that is also 0. And sine was 1, so I'm going to subtract 1 times sine theta, which is just negative sine theta. So this is negative sine theta. So minus sine theta. So cos theta minus sine theta, C would be your answer. So that's one way of doing it. I want to show you, since this is a multiple choice question, how I would do this on my calculator. So let's just pull up our calculator. I want to show you how you could do this on there. Okay, so I'm in radians. I can see that up there, but you have to make sure you're in radians. So I'm going to go into my y equals and just clear everything out that I have in there. And let's just actually put in the question. So the question was sine of pi over 2. So I'll put that in, of pi over 2. And then subtract x, close brackets, plus, and then we're going to do cosine of pi over 2. So again, that's pi over 2. And then we'll go plus x. I'll make it bigger in just a minute. I just wanted to make sure that I've got everything. There we are. Okay, so there is my question in y1. So I have my question in y1, and I'm just going to put each of my options here in y2, 3, 4, and 5. If I were doing this on the test, I would just do them one at a time, but just to save the trouble, I'm just going to put them in all at the same time and then go into your table and show you what it would look like. So this is 2 sine, oh, I forgot my x, oops, or I forgot my sine actually. Let's go back and try that again. Okay, so 2 sine of x, and then close your brackets. The next one is 2 cos x, 2 cos of x. And then I have cos x minus sine x, which I know is my answer, minus sine of x. And then the next one is cos x plus sine x. So cos of x plus sine of x. Close my brackets. Okay, let me make that bigger so you can see it. So here's my question, and then option A, B, C, and D. So don't look at the graph because it's going to be a real big mess. We're going to go into the table because remember, the check always happens in the table. And it doesn't matter where we started at, okay? So you can see this is the question here. So I can see it doesn't equal y2, so A is not an option. It doesn't equal y3, B is not an option. It equals y4, for all of them, which means C is the option. And just to go over and show you y4, or y5, sorry. Y5 starts with, it's mostly negatives to start with. And then we know that y4 already matched y1, so you can see that it also doesn't equal there. So y4 is the correct match, which means that C is the option. So if there's ever something like that on a test or a diploma, multiple choice question like that, use your graphing calculator to your advantage. Okay, I can do the same thing here, but now that you've seen it, I won't go through every question. I want to do these algebraically. So the expression 1 plus cos of 2 theta over sine 2 theta, where theta can't be multiples of pi over 2 for the restriction, is equivalent to which of the following? So I need some double angle identities there. So again, if I were doing this, I would do it on my calculator. It's faster, but just as a review, I'm going to do it algebraically. So I have 1 plus, I'm going to leave cos 2 theta, over sine 2 theta, which is 2 sine theta cos theta. So looking at the top, I have 3 choices for my cos 2 theta. So I could put in any one of these options. So for example, if I put this in here, I could simplify, but it'd be a bit of a mess because I'm having 1 plus, I'm basically having a trinomial over a monomial. I don't think that would work very well. This one here, I think this one here is the good one to use because the negative one here would cancel with the one that I already have there. And then I would just have monomial over monomial, which is what I think I'm going to do. So 2 cos squared theta minus 1. So I replace cos of 2 theta with that. And as I said, 1 minus 1 is gone. Okay, so we're left with 2 cos squared theta over 2 sine theta cos theta. So you see the 2's cancel, and cos squared cancels with this cos. So we're just left with cos theta over sine theta. And you'll see that's not one of the options because they went one step further and called that a cotan theta. So A would be your answer. Okay, over here, sine theta equals 2 cos theta, where theta is between pi over 2 and pi, in other words, in quadrant number 2. Then the exact value of tan 2 theta is what? Okay, so tan 2 theta, I need my formula. Now, notice with tan 2 theta, it's all just tans, and I'm given sine equals negative 2 over cos. So I'm going to start with that and just manipulate that formula a little bit. Now, I've told you before, you cannot divide both sides of the variable or of an equation by a variable, and cos theta is no exception. It's a variable. So what I'm going to do is I'm going to go to what I know tan theta is, and tan theta is the ratio of sine over cosine, and then I'm just going to make my substitution here. Instead of sine theta, I'll use negative 2 cos theta. So that means that tan theta is negative 2 cos theta over cos theta. Negative, I forgot my negative. And then the cos thetas cancel, so I know that tan theta is just negative 2. So if I want to find the value of tan 2 theta, I'm just going to apply that into my formula. So tan of 2 theta is 2 tan theta over 1 minus tan squared theta. So that will be 2 times tan theta over 1 minus tan theta squared. So that's going to be negative 4 over 1 minus 4, which is negative 4 over negative 3. And of course, 2 negatives make a positive. So my answer will just be 4 over 3. Okay, so 6.1 and 6.2 really lead nicely into 6.3, which is proving identities. So we're going to use all of those formulas and rules that we learned in the previous sections to now prove an identity. Now, speaking of identities, everything on your formula sheet is an identity. It's already been proven. That's why it's called a formula. So once it's been proven, we can use it for everything. So these formulas have to come out of proofs, like Pythagorean theorem, a squared plus b squared equals c squared. That came from a mathematical proof. We just take it for granted because it's already been proven. So that's what we're going to do right now, is we're going to look at identities and we're going to prove them. Now, let's talk first about verifying. What does verifying mean? Verifying is just just checking it out. So this is a potential identity right here. And I want to just verify it for 30 degrees to see if it has the potential to be an identity. So let's look. Sine of 30 over 1 plus cosine of 30 is equal to 1 minus cos of 30 over sine of 30. Okay, so 30 is a nice point on the unit circle. I've listed it there. So let's use our unit circle to figure this out. So sine is a half 1 plus cos of 30 is root 3 over 2 equals 1 minus cos of 30 all over sine of 30. Okay, so notice that I have a whole bunch of fractions here and they're all divided by 2. So I'm going to multiply the numerator by 2. And to be fair, I multiply the denominator by 2. That's going to get rid of all my fractions. And it's fair because 2 over 2 equals 1. Same thing over here, multiply top, multiply bottom. Okay, so in the numerator, I'm left with 1 over. Now I distribute this in. 2 plus the 2's cancel, root 3. I want to know, is that equal to, distributing the 2 in here, 2 minus those 2's cancels, root 3, over the 2's cancel 1. That doesn't look like it's equal, does it? Well, looks can be deceiving because I'm going to rationalize the denominator on the left side. So they don't look equal, but let's just do a little trick here to see if they are actually equal. Okay, so in the numerator, 2 minus root 3 times 1 is just 2 minus root 3. In the denominator, I've created a difference of squares. So 2 times 2 is 4. I'm going to have a 2 root 3 and a negative 2 root 3, so those cancel. And then I'm just left with negative root 3 times root 3, which is just 3. So this is really 2 minus root 3 over 1, because 4 take away 3 is 1. And now it is equal. Okay, so now that the left side is equal to the right side, I have verified it to be true. So since left side equals right side, the identity is true when theta equals 30. Okay, well, let's just show you this on the calculator. Okay, so on the calculator to check, I'm just going to do exactly what I did, punch it into my calculator. Okay, and I get the same value. So since I get the same value, the identity is true for 30 degrees. But does that mean it's true for all values of theta? Because just because it's true for 30 degrees, maybe I lucked out and just guessed the first one that was right, but all the other ones are wrong. Well, I could verify it on my graphing calculator. So I could put left side in y1, right side in y2, and then look at my table. Oh, it looks like it's true there. I do have some errors. So y1 is not true when cos plus 1 equals 0. So that's why there's an error right here at 180. And this one here is not true when sine is equal to 0. So there's an arrow. But it looks like it might be true for the ones here. But again, did I just get lucky? So it seems to be true for the permissible values. But is it true for everything? So if I can't prove it with a specific value, or in this case graphically a lot of specific values, I have to go through and look at another way of doing it. So this is just verifying. Substituting a specific value in or graphing is just verifying. It is not proving. So please remember, verifying is not proving. We're going to talk about proving. What proving means is we are showing it's true for every single permissible value possible. So we're not plugging in specific values. We're solving for all x. So we're going to leave x as x. We're not going to put specific values in there. We're going to manipulate one or maybe both sides of the equation or the identity to show that the left side equals the right side. Now, because we are proving identities now, we are proving them true for all permissible values. So you guys don't need to worry about stating the restrictions. Okay? Now, I've done a lot of proving in my career as a teacher and as a student, and I came up with a list that kind of works most of the time. This isn't every way, but this is most of the time. This is what I try and do. Okay, so first of all, I have to work on one side or the other, never across the equal sign. That's really important. Okay, and then just look, have your formula sheet out and look for those obvious substitutions, like sine squared plus cos squared is 1, or tan is sine over cos, those kinds of ones. Always work on the more complicated side. And I find that the majority of the time it works really nicely to work in terms of sine or cosine. I also look at combining fractions using a common denominator. Sometimes I'll multiply by a conjugate, or I look for common factors. So this is by no means an exhaustive list. It's just kind of what I try. Now, proving trig identities. When we're proving a true for all permissible values, never working across the equal sign, we always end our proof saying left side equals right side, okay? Now, there's also another way that we end it. There's two different ways that we are going to end our proof. So let's talk about the good way. So I took a lot of proving courses in university, and my more traditional professors would always end every single proof by QED, which is the Latin phrase, and it literally translates to what was to be shown. In other words, we have done what we were asked to prove. So it's how you end the proof. So left side equals right side, and then they would end it as QED. That was a good way of ending it. But in my opinion, because I try to be a little bit more fun, I had this prof that ended every proof with Bob's your uncle. And so I looked into this a little bit more. It was like kind of like, yay, we're done proving, because some of our proofs were really ugly. And it's a nice way of ending the proof. It's a UK phrase, which really translates to, and there you have it, or the result is reached. Okay? So this is really similar to that French expression, voila, or the American expression, piece of cake. And it's a nice way of ending your proofs. So Bob's your uncle. So like I was when I heard this, I was wondering, like, who is Bob anyhow? Where does this come from? Because it's a really common phrase to end proofs. Bob's your uncle. Well, here's Bob. Rather good looking young fellow, isn't he? Who he is, his name is Bob for short. It's actually Robert Cecil, and he was a prime minister in the UK. Now, when he was a prime minister, he appointed his nephew Arthur to be the chief secretary for Ireland for no good reason. And people were up in arms about this. Like, why is he getting this promotion? So it was a very unpopular act of nepotism, which is just showing favoritism to your family members. So the joke in the UK was, why did Arthur get the position? Well, because Bob's your uncle. And that's how the phrase was born. So because I really liked my fun math professor in university, ending it with Bob's your uncle, I cannot in good faith end a proof without saying Bob's your uncle. So let's try our very first proof, okay? So we verified this proof with 30 degrees. We verified it graphically. Now we're going to prove it, which is true for all values, okay? So the very first thing I do is put a line down my page because I need to remind myself I can't work across the equals sign, okay? And then what I'm going to do is try and prove that the left side equals to the right side. Now, it does not matter which side you start on, left or right. I'm going to start on the left-hand side. And the thing with proofs is there is more than one way to prove. So don't think when you're doing a question just because you didn't do it the way I did it means that your way is wrong or my way is right. That's not true at all. There are a couple different ways you could approach a proof. So what I'm going to do is I'm going to multiply numerator and denominator by the conjugate. Okay, so I'm doing this for the benefit of the denominator, so I will leave my numerator in factored form. Now I did this because on the denominator I'm now creating a difference of squares, so 1 times 1, and then I'm going to have a cos x and a negative cos x which cancel, and then minus cos squared. Now remember, I got you guys to rewrite all those Pythagorean identities in different ways. Here's why. 1 minus cos squared, well, that's really just sine squared. So it's being able to recognize all your trig identities even if they're written differently. Okay, and then I see that sine x canceled with the squared, and I'm left with 1 minus cos x all over sine x. And you can see I have a match, and that makes me really happy. Tells me that I'm done it, but we're not done the proof yet. Here's the most important step. Left side equals right side, so Bob's your uncle. Okay, now I'm just being silly. I have to end my proofs with Bob's your uncle. I'm okay if you just want to stick to left side equals right side. But if you want to spice it up and have a little bit of fun, end it by adding also Bob's your uncle. And if you do that in university, your profs will get a big smile on their face because you know that. They'll be so impressed that you know that. Okay, let's look at this one here. Prove the following identity. Sine squared over cos squared plus 1 equals secant squared. Okay, so again, I draw a big line down my paper. Not really a lot to do on the right-hand side, so again, I'll start with the left-hand side. And I think what I'm going to do here is add them with a common denominator. So I'm going to add a common denominator of co-squared because this is really 1 over 1. So if I multiply this by co-squared, I'm going to multiply that by co-squared because co-squared over co-squared is just 1. And it's really interesting. Every time I do these proofs, I don't always solve them in the exact same way. So I just really want to emphasize that there's not one way to do a proof. Okay, so just do it the way that your mind goes to. So I add them together now that they have a common denominator, and then sine squared plus cosquared, hope you recognize that as a Pythagorean identity of 1 over cosquared. And then 1 over cosquared, of course, is secant squared. So those are equal, and again, that makes me happy. So I'll just end my proof by saying left side equals right side, so Bob's your uncle. Okay, let's try this one here. So, ooh, this looks fun. Sine squared plus sine squared times cotan squared equals 1. So I'm going to, there we go, draw a big line down my paper. And on the left-hand side, I notice both those terms have a sine squared. So I'm going to try and factor that out, see what that gives me. So sine squared x, factoring that out, I'm left with 1 plus cotan squared. And it's equal to 1. So 1 plus cotan squared, that must equal to something. So I'm just going to refer to my formula sheet. 1 plus cotan squared. Ah, there it is. Do you see it right there? 1 plus cotan squared is cosecant squared. So always have your formula sheet close at hand. So that's cosecant squared. So this is sine squared x times cosecant x squared. Now, cosecant squared is just the reciprocal of sine squared. And then hopefully now you see the sine squareds cancel, and I'm left with 1. So those are the same. Again, that makes me happy, although that kind of looks evil, but it's actually happy. And then end it. Left side equals right side, so Bob's your uncle. Okay, let's do another one here. So again, big line down the paper, and let's see what we're going to do here. This kind of looks like that first question I did where I did conjugate, and since that worked out so well, I'm going to try it. But just for fun, I'm going to do the conjugate of the numerator this time, just so you see a different way of doing it. Okay, so let's instead multiply by the conjugate of the numerator here, and just see what we end up getting. Okay, so I'm going to leave my left side alone, and on the numerator I've created a difference of squares, which is 1, and then negative sign and positive sign cancel, minus sine squared. And remember, we're doing it for the benefit of the numerator, so leave the denominator factored. Okay, 1 minus sine squared, that's just cos squared. Pythagorean identity rearranged. And then I see that the cos squared and the cos cancel, so I'm left with 1 over 1 minus sine x. No, I missed the cosine, silly. There's a cos still there. There we are. I just got rid of the squared, not the cos. So cos x over 1 minus sine x. There we go. Now they match. And those are the same. Okay? So again, every time you do this, you might get a different way of doing it. Okay? But left side equals right side, so Bob's your uncle. So this should give you some comfort that there's not just one way of doing it. Okay? So it's whatever way you want to do it. Okay, let's try another one here. Okay, so for this one here, 1 minus cos squared equals cos squared times tan squared. So big line down there, and let's see what we do. So I'm really tempted on the left side just to write that right away, 1 minus cos squared as sine squared. That's just a rearrangement of the Pythagorean identity number 1. And then over here, I'm going to multiply tan squared is the same, well, tan is the same as sine over cos, so tan squared is the same as sine squared all over cos squared. And then the cos squareds cancel. Oh, that was a really short proof, wasn't it? Okay, and there we go. They are the same. Makes me happy. But what makes me happier is to end it with left side equals right side, so Bob's your uncle. Okay, another one here. So this one here looks really fun, doesn't it? Lots going on here. So let's do a big line down the middle. And I think we should start with the right-hand side. Just kidding, because there's only a cos there. What can you do with a cos, right? We're going to start on the left side. And what I'm feeling right now is let's write it as sines and cosines and see where that takes us. So secant is the same as 1 over cos. Sine is just sine. And then cotan is cos x over sine x. I feel really bad for this sine x all by itself. I'm going to put it over 1 so that it joins the group of fractions. And then tan x, I'm going to write it as sine x over cos x multiplied by cosecant, which is 1 over sine x. Now let's just see if there's things that we can cancel. I see there's some things in the numerator, like dividing by cosine and multiplying by cosine is 1, multiplying by sine and dividing by sine is 1, so that whole numerator is just 1. And then over here, the sine x divided by sine x is 1, so I'm just left with 1 over cos x. Don't write it as 1 over cos, because we still have this numerator, and this is still in the denominator. So 1 divided by 1 over cosine, well, if I just multiply top and bottom by cos to get rid of the denominator, it's fair because I did it to both, I just end up with cos x over 1, which is cos x. So it's a good thing we started with the left side, isn't it? So those match, and that makes me happy. But what makes me happier is saying left side equals right side, so Bob's your uncle. Okay, so another one here. Prove the following identity. Secant over sine minus sine over cos equals cotan. Okay. I think what I'm going to do here is common denominator. So looking at this, I'm going to write it as a common denominator of sine x and cos x. So in fraction number 1, to make this the same, I would multiply top and bottom by cos x. So I'm going to have cos x secant x minus, and over here to make them match, I would multiply top and bottom by sine x. So sine times sine is sine squared x. Okay, so that's secant x is kind of sticking out to me. So I'm going to rewrite this as cos x times secant, which is 1 over cos, minus sine squared all over sine x cos x. And then that's gone. Okay, so I'm left with 1 minus sine squared all over sine x cos x. So looking at this, this is a rearrangement of Pythagorean identity number 1. So 1 minus sine squared. Anytime you see a cos squared and a sine squared put together with a 1 and subtracted, I'm hoping that you go to that first Pythagorean identity. So that's just cos squared over sine x and cos x. So my squared cancels with my cos. So I'm left with cos over sine. Oh boy, I hope that matches all the way back up here. Oh, cotan, it does. So because I don't have a lot of room there, I'm going to go up here and say that cotan is cos x over sine x. And now, let's just make that whole page bigger. There we are. Those are a match, making me very happy. And therefore, I can say that left side equals right side, so Bob's your uncle. So hopefully you guys are getting really comfortable with this idea of proving. Every question is going to be different, but you see a lot of those strategies that I gave you before are going to help you work. So again, with proofs, never work across the equal sign. Do that big T shape like I do so to remind yourself. Start with the more complicated side, and usually writing things in terms of sines and cosines really helps. Don't worry about the permissible, non-permissible values because we're proving true for all permissible values. So end your proof with left side equals right side, and if you want to be super fun, end it with also Bob's your uncle. So I think after today's lesson, I can officially retire from teaching because let's be honest, I have nothing left to prove. You guys can go ahead and do practice question number 1, and there's different parts of it. Detailed solutions, of course, are on D2L, and then you can go to your textbook question. I hope this video helped, and I look forward to seeing you for the next one.